Good morning, mathematicians. Getting early start to the day again. Hope you've been well. We're in the middle of the week. You should be at the prime of your theorem proving. Actually, you should be at the prime of your theorem proving every day of the week and the weekend. In your sleep, even. You should be proving theorems. If that's not the case, I'm disappointed in you. You gotta work harder. Good morning, Edit Smith. So timely, so on the ball every time. Okay, what should we start with? Some Reddit news, possibly. I saw that Veritasium made a new axiom of choice video. Well, I should say made axiom of choice of video. I don't think he had one before, but new in the sense of all videos. Haven't done any math in like 3 days. Oh my god. Now I'm upset. Now, I was planning on having a good day today, and then you tell me this information. Hello, Mustafa. Yeah, let's see what's going on. Compilation of this person's favorite theorems and problems. Nice. Halting problem, classic. Oh, wait. Oh, yeah. I remember. Oh, yeah. This is that's a joke post. Right. Motivation. Sad you missed the octonic algebra talk. What was that about? Well, you can always the upload's always there. You can always go check it out. But the TLDR is I was just talking about the fundamental theorem of algebra for octonions, and a paper that proves it using topological K-theory. Well, really, I mean, I guess it does, but it's mostly just facts about vector bundles. And then, of course, the famous theorem that, what is it? Relation between division algebras and spheres. Oh yeah, I think I even looked at this exact Stack Exchange post. No, there's got to be like a wiki article on this or something. Cedarval. Yeah. Anyways, it's the fact that the existence of I bet you NLab will say something about it because it's algebraic topology. Yeah, here we go. Division algebra, classification. Oh. Interesting. I guess I knew that because I guess that's one way. I guess that's one way you can define p-adic G2 as well. Give a model for p-adic G2. Let's see. I thought they would talk about the connection to the spheres. Maybe they do. I'm just not seeing it. Oh well. There's some connection to parallelizability of spheres. I wonder if I should run to my room and get Peter May's book. Oh, well, here it is. Hopf invariant 1 problem says that the only continuous functions between spheres of this form whose Hopf invariant is equal to 1 are the Hopf constructions on the 4 real normed division algebras. There we go. There we go. Yeah. Maybe I should just jump back into D modules. Yeah. I thought about making it's definitely sort of like clickbait content farming, view farming type content, but I thought, there's some cranks on YouTube And part of me doesn't really want to start a war with the cranks, but it would really drive up engagement. So I thought about making some videos. There's debunking, making videos debunking their things. But I don't know. It's kind of annoying to be that person. It's like it's like, why would I spend my time arguing with someone that can't be reached? I guess maybe there's value in that, you're combating other people looking at their stuff and getting confused or something. But are you really? I don't know. Cranks do be cranking. Well, maybe we should just jump back into D modules then until there's other questions. I wasn't planning on teaching myself D modules live on stream, but here we are. Where were we? What is your goal with learning D modules, if I may ask? Well, not so clear. I mean, yeah, the thing is, well, yeah, so normally, well, I just turned it away, but the Riemann-Hilbert correspondence tells you that there's an equivalence of categories between, well, I guess the derived category of regular holonomic D modules and the category of perverse sheaves. And I work with perverse sheaves. Actually, in fact, I work with something called equivariant perverse sheaves because there's some group action that it respects. And I mean, D modules would just offer another perspective for computing these things. Previously, someone who studied under my supervisor tried to take the approach of D modules, and I think we ultimately ended up staying with perverse sheaves because there was some, I don't know, roadblocks that were harder to compute with D modules, is my understanding. But the thing is, there's some things we're doing with perverse sheaves that enter the world of micro-local analysis and / micro-local geometry. And we have someone at our university who I guess she works in a few different areas, but she knows stuff about this. And we're just trying to make use of the local resources we have, being people that know things about that. And connecting with her and finding a common point, because we're more, she's more of an analysis, we're more of algebraicist, so we're trying to find a place where we can understand each other and then hopefully work from there on some projects. That would be the dream. That's the goal. And I mean, we might just end up, I don't know, learning stuff. But yeah, we have sort of semi-specific goals. And I mean, there's more specific things that we're trying to do, things that we're trying to compute with micro-local geometry. In particular, there's something called the vanishing cycles functor of perverse sheaves. And there's computations that we're trying to do with this. And well, the version we use, there's like a very algebraic definition of vanishing cycles, but there is also an analytic one, and and somehow like the analytic one is connected to the theory of like Morse groups, and Morse homology, which is a perspective on these things that, again, we just like we know is there, but we don't know those tools. And so if we can move closer to understanding those tools, I mean, maybe it will just give us more methods to attack the problems that we're interested in to do with these vanishing cycles. Yeah. I don't want this to just become a demodule stream, though. I want this to remain my general office hours, where I talk about random stuff, and yeah. But I guess it's on me to come up with new stuff to talk about each day, until people have questions. Any chance that I have tips on how to intuit geometric Satake? I was hoping to get my hands on some actual examples that can be written down, but can't find anything. Yeah, I haven't really. So speaking of, just by the way, buy this book. just buy this book. Everyone in the stream, buy this book. I swear, I'm not being paid by Professor Chard. But speaking of, Chapter 9, the geometric Satake equivalents. Yeah, I mean, to be honest, I haven't really learned this. I've opened this chapter and I've flipped through it, but yeah, I'm familiar with the classical Satake isomorphism. And I understand that this is somehow supposed to be a grand generalization of that, but yeah, I don't know. I certainly haven't worked through an explicit example of this myself, but I mean, maybe there's something hidden here in the exercises. Let's see. Yeah, I mean, I think there's a few things that are going on once we get to this sort of like categorical local Langlands stuff, like, and keep in mind, I'm saying this as someone who's not an expert. Part of the advantage is that certain things become more natural. Because we're able to use, well, categories and the affine Hecke algebra, extended affine Hecke algebra gets categorified, and we can, I mean, there's then very natural operations with like sheaves and derived functors, and we can go to higher categories as well to make constructions like more loose. But my impression, okay, this might be something along the lines of this looks like it's possibly connecting the classical this looks like it's connecting the classical Satake isomorphism to this stuff. Having a hard time with perverse sheaves in general, to be honest. Can't really wrap my head around them, how to work with them without just pretending they're regular sheaves. Yeah, I mean, that's what I do. Yeah, I mean, the way that my research, the way that I learned perverse sheaves was first as an engineer, which is to say what we do. The way I learn them is like the the way you learn calculus. In North America, I should specify. Other countries do it properly, but in North America, one generally just learns these rules of differentiation, but one never properly defines a limit. Typically, this is a very common thing in North America. And then only later, once you've gotten, you've developed a skill at performing integration and differentiation, do you learn the theory behind it. So this is how I learned the theory of perverse sheaves. So so some of your tools are going to be the fact that, well, so suppose you have some variety, and it's stratified by some, you've got some stratifications, and you've got, so what are your perverse sheaves? So your simple perverse sheaves. Well, first off, by the way, so if this is some stratification, right? So X is some, union of the C, and I think we want all the C to be locally closed. Then the idea is that the simple perverse sheaves. I saw the question about main objects of study in my field. I'll list some of those off in a minute, but let me finish a few thoughts here. So the simple perverse sheaves. So maybe you know this, but like the perverse sheaves, these are a subcategory of the bounded constructible derived category on X. But in particular, it's an abelian category, so we can talk about its like simple or irreducible objects, and so everything's going to be like built out of those. So a simple perverse sheaf is going to be given by the intersection cohomology complex, where it's attached to one of these strata, C, and some irreducible local system, L, living on that strata. And this thing is defined, there's some, like, you use, I can't remember the intermediate extension. It's like you take the intermediate extension, whatever that is. So I'm going to try and convince you in a second it doesn't matter. I mean, you should go read the definition eventually, but where it's defined to be the intermediate extension, and you shift by the dimension of C, right? And so of course this functor here, I mean, this is a derived functor, so in general, when I say start with a local system, really we're pretending this is a complex with just a local system concentrated in degree 0, and then we apply this derived functor, and in general we'll just get some other complex, and then so it's a theorem that this will be a simple perverse sheaf. Okay, well, that's not very enlightening, but instead of, I mean, certainly there's times where I in my research, like, compute explicitly what the equivariant, what the perverse sheaves are, but more often than not, I'm just interested in the stocks of these perverse sheaves, or rather, their restrictions back to strata. So what I mean by that is remember that the what it means to be in the constructible derived category says that, so not only are you some complex, but given some complex, we suppose that if you took cohomology of that complex, and restricted it back down to one of the strata, that you just return a local system on that strata. So the way that I understand like an individual perverse sheaf is basically just by doing this. I take some perverse sheaf, and you look at what happens when you restrict it to each of the strata, or rather its cohomology restricted to each of the strata. And more or less, I just like, and in fact, this is the Kasdan-Lustig hypothesis itself is just precisely about this table I'm about to draw. I'll just make a table. So let me give you an example, just to sort of illustrate this idea. So suppose we have A1, like just the complex numbers, and let's write it as stratification of two spaces, right? So we'll just take the point and the non-zero complex numbers. So these will be our two strata. And in this particular case, I'm going to I'll just consider the trivial local systems on each of these strata. Okay, maybe I'll have to like explain some of these calculations, but for now, let me just tell you what the result is. So it turns out if you take the so here I'll put IC of 1, here I'll put IC of 1, and here I'll put restriction to this orbit and restriction to this orbit. And so it turns out what you get is something that looks like this. There should be a 0, and this is a 1. Right. And so generally, this is how, in this case, it is possible to explicitly to like figure out, I mean, basically, I think you can just use some like adjunction pushing to figure out what the ICs are a little more explicitly. But this is the normal process of what I do to understand a perverse sheaf. Is I just make these tables where you're taking your perverse sheaf, you're restricting it back down to the orbit, and you're seeing what the orbits are in there. I should say, I misspoke slightly. You'll get a shifted local system. So you'll end up with well, actually, sorry. I lied. It's not true. Once you take cohomology, you just get an honest to God local system back. So sorry, what I said originally was true. But usually the way that I write things is I keep track of the shifts. So then I can sort of see like what's living in what component. So actually, you can see from the way I've written this, I mean, this is kind of an unfortunately simple example. Both of these complexes are concentrated in a single degree in this case. Is that true? Wait, am I lying? Yeah, they're both concentrated in a single degree in this case. And in fact, I mean, this is what the Kasdan-Lustig hypothesis, the p-adic Kasdan-Lustig hypothesis, says that if you take the transpose of this matrix, well, you replace each of these sheaves with you just write the dimension of them. So I mean, these are all one-dimensional local systems. if you says the transpose of this matrix, it gives you the matrix that tells you the multiplicities of irreducible representations in things called standard representations, by the way. Yeah. So, okay. This is one way to view it. And the thing is, there's also tricks, right? So, like if, for example, proving bijection between a compact space and the set of maximal ideals on the ring of continuous real-valued functions. Okay, we'll get to that in 1 second. I want to rant more about perverse sheaves. I'll pause on perverse sheaves for a second, address more of the questions in chat, and then I'll probably come back to perverse sheaves. But let me just mention that there's some tricks where so if you've got some, if you're on if your strata is open, right? If this is open, then I believe, what is it? If you take a local system, you take some local system on the closure of that strata. Now you restrict it back down to the open, and so I'm gonna let J be the inclusion into your whole space, and now you take the intersection cohomology of this thing. This will just be the underived proper push forward of your local system shifted in the dimension. So, for example, that applies here, right? Because CX was open, and of course, we can just take the constant local system on everything, restrict it down to the orbit, and then this result says that IC of did I say this right? Yes, but the proper push forward, it needs to pick up a stock. It needs to pick up a stock at the origin. There's a chance I'm being silly right now. There's always a high probability of me being silly. Right, and this is one dimensional, hence the shift by one. Yeah. So let me just yeah. So let me just say there's often tricks like this where you have theorems about if the closure is smooth, for example, there's stuff about restriction. And then maybe I'll just quickly mention, maybe for tomorrow I can even prepare something a little more coherent and actually do some computations with perverse sheaves. Your best friend is the decomposition theorem. At least that's something that I'm using a lot. It really helps you. It really helps you do these computations. Basically, what happens is, so you want to know, you've got this IC, right? You've got this IC of some local system. The name of the game is we want to restrict this back down or take its cohomology at each of the other strata, and that's how we're going to understand it, is just look at the stocks and see what local systems are showing up in there. And the thing is, so there's nice theorems when C bar is smooth, but when it's not smooth, then we have some more problems. So the idea, the general way that we play the game is that we take a resolution of the closure, and We then take a push forward. So I think so let the P be the projection map. So I think like proper derived push forward of the constant sheaf. So this thing is smooth, and when your space is smooth, all your perverse sheaves are just shifted local systems. So we just take the constant local system, shifted in this dimension, which makes it a perverse sheaf. And the decomposition theorem tells you that this will be a direct sum of your simple perverse sheaves. So that's just going to be a direct sum of like ICs as you range over like orbits and local systems, with some multiplicity, each of them. And the advantage here, so I know this seems complicated, but yeah, maybe tomorrow, maybe even, yeah, I don't know. Well, we'll see how much time there is today, but maybe tomorrow I'll like do some actual down to earth things, because I'm maybe not convincing you. I don't know if this is helping, but basically what you can do is then, well, you can apply cohomology to both sides of this equation, and look at the stock. And so basically, when you apply cohomology to this side of the equation and you take a stock, you'll basically get at least, so if we forget that there's like structure of perverse sheaves and whatnot, we just think about it as like a complex, like a graded vector space, basically. This side of the equation will just reduce to computing the cohomology of the fiber. And so why does that help? That helps because if you've like chosen this map well enough, you should be able to compute the cohomology of this fiber. And then you'll just have, you know, some like graded vector space over here, basically. You know, look something like this, maybe. So then, you know, when you go over here and you do the same thing, you take cohomology and you take a stock, you know that you need to match up those stocks in the appropriate degrees so it matches this side of the equation. And then you can basically do some linear algebra, more or less. You do this several times with different orbits. You get basically like you have to match the dimensions in the appropriate degree here to these multiplicities. That gives you a bunch of equations. If you have enough equations, you can find a unique solution to it, and then it basically tells you from there like which of the like graded vector spaces corresponds to which sheaf. Okay, that's a really yeah. Yeah, maybe tomorrow. Perverse sheaf is not always semi-simple. No, it is for affine Grassmannian. Oh, interesting. I actually didn't know that. So in the case the theorem is immediate, yeah, no, it is not true. It is definitely not true that perverse sheaves are always semi-simple. Absolutely not. But the claim, the sort of the decomposition theorem tells you that at this push forward will be semi-simple. Okay, let me go back to some of the questions. So what are the main objects of study in my field? Well, you just heard me ranting about perverse sheaves for a while, so I would say, well, algebraic groups, over p-adic fields, specifically, representations, where, of course, these are topological representations, and they can be infinite dimensional. Algebraic varieties. I should maybe even just say complex varieties. And and manifolds. Derived categories. And perverse sheaves. And I guess for me, I deal with rings and modules. I mean, basically, the final things I need to do to complete my main thesis topic is just sorting out some nasty ring isomorphisms that suck. Yeah. I guess those are the big things, the main ingredients, main objects of study. Yeah. Okay, having trouble with proving a bijection between a compact topological space. So we got K compact. And the set of maximal ideals on the ring of continuous real valued functions. So CK. Between a compact space and the set of maximal ideals, I think the problem is you don't understand the property of compact topological spaces. Yeah. What are important questions about algebraic groups over QP that has been answered in the past, and what's left? Well, I don't know specifically about the questions, just general questions about algebraic groups over QP. But well, the questions that are the questions that there are to ask are the local Langlands correspondence, which I talk a little bit about in a video, but maybe I'll come back to that one. Because that's fancy. It's not just about algebraic groups. It's connecting algebraic groups to number theory. Yeah. 100 years. Well, math is hard. Okay, so compact space. We want a bijection between that space and the maximal ideals of the ring of continuous functions. Well, basically, so I think the ideal that we take, I mean, well, this is more or less the insight to sheaf theory. So somehow this ideal should be defined in terms of the points of this compact space. To be clear about the problem you're trying to solve, I want to show that every maximal ideal is of that form, and you need to use that K as a compact topological space. So we've got, right, okay, so you already know that. So for all P, we have the ideal at P, defined to be all of those continuous functions which vanish at P. Okay, so I guess you've already proved that those ideals are maximal. And you want to prove that those are the only ones. Actually, I'm not sure how this proof goes. I forget how this proof goes for compact topological spaces. I do wonder it might involve some functional analysis, right? Like it might involve producing some sequence of functions. But well, then again, all our maximal ideals are of this form. I mean, the idea. Fundamentally, if K is compact, like we want to use, it has something to do with the fact that if it is 0 on a point, it is 0 on some open neighborhood. Basically, yeah. I mean, yeah, yeah. Well, one generally considers the stock, and the stock we normally think of, right? The stock is the collection of all germs, which are all pairs of functions u and f, such that um, u and f, such that what do we need of f? Oh my god, I'm blanking. Oh, I think we just need that. So the stock at P is that P is contained in U. Yeah, and F is just a continuous function on U, and then we say that a pair are equal. The pairs are equivalent if and only if there exists a subset of the intersection such that these restrict to equal functions. Well, I mean the yeah. So, anyways, probably what like the way to go is, of course, we want to somehow use the fact that K is compact, right? And so, well, what does it mean to be compact? That means every cover has a finite subcover. Well, my intuition is telling me that this isn't this. I mean, okay. So, I mean, my first thought is, because this is the definition, simply like the goal is to somehow come up with an open cover, right? So I would start with start with a maximal ideal. Start with some maximal ideal in here, and we're going to want to build an open cover. So probably we'll do something. I mean, just borrowing from algebraic geometry is like, think about like the zero locus of polynomials that generate this thing. So, I mean, something like that is the first thing that comes to my mind. But then again, I mean, we are talking about spaces of functions on, a ring of functions on a compact space. And so, we do have more stuff going on, right? We've got like our soup norm, and we've got a topology on this space itself, and my guess is probably life is easier if we prove something using actual functional analysis here. How do we get a big picture of a field in math, for example? Since you're interested in algebraic geometry, algebraic number theory, you heard of the name like Schulze, but even I read the explanation, still don't get why his work is important. Yeah, I mean, the thing is, there's just certain stuff you're not going to be able to understand until you have sufficient experience, right? Like, I don't know. Say, okay, Schultz has got a paper where he defines the pro-étal topology, and and the benefit of that is that What is the benefit of that? Uh, somehow it's better for certain purposes, let's say, than the ordinary. Actually, I forget I used to have the one word. My memory's getting worse. But okay, whatever it means, is he's got a paper where he introduces the pro-etal topology, and it's just a better suited topology for doing certain kinds of computations. Oh yeah, I think right. I think the advantage of it is that the usual cohomology theory for the for étal sheaves ends up like you end up having to take some limits of sheaves or something. Whereas if you look at the pro-etal site instead, then you get like this honest to God sort of abelian category, and you can sort of do the cohomology theory directly. This is my vague recollection. I'm most likely saying something wrong here. Anyways, probably a lot of those words meant very little to you, right? And you're like, okay, cool. Why would I care about any of those things? So it's going to be hard to explain any of that stuff until you've reached a sufficient level of sophistication. So the only way to do that is to keep learning more math. Yeah, I mean, keep trying to read his papers and like go look at the words that are there. I mean, if you look at the introduction to some of his stuff, there's explanations, but yeah, I mean, probably at this point, from where you're starting from, it's just layered on. It'd be like, oh, he'll say this is a really great breakthrough because it allows us to do this other complicated thing that you don't understand, and you'd be like, okay, but yeah, the only way is just I don't know. You gotta learn more. There's no quick way. There's no quick way. So yeah, keep working on your interests. Anyways, okay, so we've got our maximal ideals. Is it really supposed to be that the maximal ideals are in bijection with the? I mean, I suppose so. Like, the other thing I'm wondering too, it's been so long since I've thought about this. The other thing I'm wondering too is that, like, because we're dealing with a compact space, I wonder, do we have theorems that say like these ideals are the maximal ideals are finitely generated? And this is where I'm wondering where the functional analysis comes in. Like maybe that's what allows us to prove that these maximal ideals are finitely generated. Because then if they are, if the maximal ideals are finitely generated, I would do something like I would say, well, take the generators of this maximal ideal. It's zero locus. It's zero. The common zero locus of these polynomials is surely going to be closed, and therefore this complement will be open. Yeah, it's hard to care about tough answers without already caring about the problems themselves. Yeah, exactly. Personally, I don't think there's a point forcing yourself towards some area of math just because a lot of people talk about it. Yes and no. Yeah. I mean, you shouldn't well, I don't know. Like, you do have to do what you enjoy, but also at the same time, I mean, I don't think you also shouldn't ignore what's popular, right? It's like if you choose to go into set theory, for example, and don't get me wrong, I love set theory. I think it would be a cool thing to study, but it's not very popular. It's not a big flashy thing that a lot of people care about right now, and so you're going to have a hard time. Like, I remember when I was applying for grad schools, there was one professor I talked to, and I was interested in what he was doing because he had stuff about F1 geometry. And he was like, I messaged him to ask if he was taking students, and he was like, yeah, but, you know, just be aware, like, the thing is, no one is working on F1 geometry. No one cares about it. I mean, that's not entirely true, but, like, it's very niche, it's very obscure. You're not likely to get a job, right? As opposed to something that is like hot and flashy and like lots of people care about and are working on. So it is, I think, important to also take into consideration like what people are working on, because like there's not a lot of logicians. There's not a lot of like not a ton of people are hiring logicians, for example, as opposed to like data scientists. You should do math you enjoy, but factored into that is the fact that math becomes a lot more enjoyable when you have a community of people to get enthusiastic with. Yes, absolutely. That is also a very important consideration. You also have that any group of functions that don't have common zeros generate the entire ring. Ah, okay, yes. So, okay, so you have any group of functions that don't have common zeros generate the entire ring. I see. So, so you have, say, F1, F2, no common zeros. No common zeros. Then this ideal is the entire ring. Okay, great. Right. Okay. I'm seeing. I can see. Right. I remember this. Right. Okay. So. Well, wait a second. I mean, this should. I think this is the. I think this is the part that follows from compactness, right? Because from what I said here is basically like, well, really for each function, you can take an open cover, right? Or for each function, you should be for each individual function, you can take this closed set and then define, I don't know, maybe call it UF to be the complement, and then these things well, we have to argue it, but that should form an open cover of K. And so there should exist. Am I doing something crazy here? Yeah, there should exist finitely many. There should exist finitely many functions such that this is an open cover. And I think in fact, yeah, this is the part I was thinking of. Maybe this is the thing that gets us to this fact. You have a paper in set theory without axiom of choice last year, and you felt disconnected with the community and started pursuing commutative algebra. Oh, interesting. I mean, that's interesting. I thought there's plenty of stuff without axiom of choice that people are working on. But yeah, broadly speaking, commutative algebra is more popular than set theory, so that's just the way it is. Okay, yeah, let's think. I think I've got some. This is like basic algebraic geometry. I should have known the answer like immediately. Right. So what's my claim here? Yeah. Yeah, I mean, I think we can basically. Oh my god, I'm so tempted to just look it up at this point instead of embarrassing myself on stream even further. But oh, Jose, just give me the answer. Jose probably remembers the answer. Uh, any group of functions that don't have common zeros, yeah. And, you need that the space is Hausdorff. Ah, yes. Aha, aha. Right. Okay, but we do have that it's Hausdorff because this is not the algebraic geometry version of the story. We're thinking about yeah, K is just a compact. Okay, let me get everyone on the same page here. So the question is about the ring of continuous functions on a compact space, but by which we mean really the ring of real valued continuous functions on a complex space. And usually when people write something like this, they have in their mind that compact means secretly it means Hausdorff plus quasi-compact. And quasi-compact is probably what you think compactness means. It's the condition about the open covers. But because people just believe in Hausdorffness so much, especially analysts, usually if people are writing this, they really mean Hausdorff plus quasi-compact. And that's just sort of like, I don't know, implicit in like your analysis courses or and everything. But in algebraic geometry, we almost never have Hausdorffness. And so like you have all of these, theorems in functional analysis about compact spaces, but those theorems from your like analysis 1 or analysis 2 course about compact spaces, those are oftentimes theorems about Hausdorff and quasi-compact. But in algebraic geometry, if we're looking at spec of some like infinite ring here, this is basically the finite complement topology. So it will never be Hausdorff. In fact, it's probably not even Hausdorff for. It won't be Hausdorff in general, anyways. And so the same theorems don't apply. But okay, so this is just a little public service announcement. Like be careful. Things that you think are compact are sometimes implicitly compact Hausdorff. But sometimes we care about non-Hausdorff spaces. But in this particular example, we have Hausdorff. So yeah, I think we should have the baked-in assumption is, let's be really specific, quasi-compact plus Hausdorff. Okay, and now I don't feel so stupid because we need to use Urshan's lemma to separate points, and I didn't remember that at all. But okay, but that's also case in point. I was saying that there's probably some functional analysis we need to use here, special to K, and it's not just an algebra thing. So thank you for that. Um, you think it's totally normal that someone forgets how to do this if not directly related to their work? Yeah, yeah, but it's still nice to bust things out live on stream and feel like a giga chad, you know? I gotta like, you know, practice really difficult questions ahead of time and then pay people to plant questions and they'll be like, oh yeah, look at me go. Uh, I'm kidding. Now everyone's gonna be super sauce if I like bust out a solution to a difficult problem. Yeah. Okay. Maybe I'll look at this. I feel like I owe you guys a better explanation of this now. So I owe you this plus maybe a computation with perverse sheaves in an attempt to convince you that it's actually very, despite all the fancy definitions, it's actually very computable. Just naturally take k equals to a closed interval and try to solve. Yeah, yeah. Well, I mean, unironically, actually, a good um, it's always a good idea to, if you're trying to, you're stuck trying to prove something, take an explicit example and work there. Yeah. Well, I'm almost out of coffee, so it might be time to wrap up the stream. Um, yeah, I owe you functional analysis and perverse sheaves. Hold me to it. But in the meantime, I'm gonna go prove some theorems. And then I might climb. With a rope and stuff. So that's fun. Yeah, that's the plan. Go prove some theorems. Get some exercise. Tomorrow you're gonna put me on the spot to prove CFSGs. I don't even know, and make you look hella good. Okay, I don't know what a CFSG is. So I've already failed. Okay, anyways.